Assalamualaikum. We are from Group 4. My name is Amirul Izzat bin Shazmi Rizal. Also, my teammate.
My name is Ahmad Kasha.
My name is Ali Hakimi.
And my name is Ahmad Hazim.
We are going to present about Heritage Malay Kuih. This is our project. So, to begin the project, I needed to build a robust dataset from scratch. I choose to focus on 4 pillars of Malay heritage desserts, which is onde-onde, kuih lapis, serimuka, and tepung pelita. As you can see in my code, I use the DuckDuckGo search API to gather these images. Instead of simple searches, I developed specific queries using descriptive metadata like pendant custard or banana leaf boat to ensure the engine found the most accurate representations of each kuih. A vital step here was including the dash cartoon tag in every search by filtering out illustration and icons. I ensured that my model would only train on real-world food photography, which significantly improves its ability to recognize actual kuih in the future. The results of this phase was a clean, balanced dataset of 800 images, exactly 200 for each category, which gave the machine learning model a high-quality foundation to learn from. So next we got data engineering and the 80-20 split. Once the images were collected, the next critical step was data engineering. In machine learning, you can't use all your data for training or you won't know if the model actually worked or just memorize the picture. As you can see from the bar chart and summary table, I implemented a strict 80-20 split. I allocated 80% of the images for the training phase where the model learns the colors and textures of the desserts. The remaining 20% was set aside as a test set. These are images the model has never seen before, acting as a final exam to prove its real-world accuracy. I use a stratified approach, meaning every single category, from serimuka to tepung pelita, has an equal representation in both sets. This prevents the model from being biased toward one specific type of kuih. Next, to conclude the data engineering phase, I perform a final validation of the dataset. As you can see in the summary table, I successfully created a perfectly balanced distribution with 160 training images and 40 testing images for every single category. I also generated these contact sheets to manually inspect the data. The visual check confirms that my automated scraping process successfully filtered out noise and keep only high quality real world photos. A key technical justification for this project was the decision to use full RGB color mode. Since many Malay heritage desserts share similar shapes, the specific shades of color are the most critical features for the model to learn. This foundation is now 100% ready for the training phase.
Assalamualaikum. For my part, I will be explain the hyperparameter tuning process for our CNN model. We use Crush tuner with random search to systematically optimize the simple CNN architecture. The tuning focus on 3 main hyperparameters, which are the number of convolutional filters, dense layer units, and the learning rate. Specifically, we tested filter with value 16, 32, and 64, dense unit 64, 128 and 256, and learning rates 0.01, 0.001, and 0.0001. Each combination was trained and evaluated using validation accuracy as the main performance metrics. Based on the results, the tuner automatically selected the best hyperparameter combination. The highest validation accuracy achieved was approximately 57%, showing that the tuning process improved model performance. These selected hyperparameter were then used for the final CNN training. Next. After obtaining the best hyperparameter, we proceed with the final CNN model training. The model was rebuilt using the best hyperparameter values selected by questionnaire. Training was conducted for 10 epochs using the training dataset and validated with the validation dataset. During training, both accuracy and loss were monitored to evaluate model performance and learning stability. Once the training process was completed, the final trained CNN model was saved as model underscore CNN point #5. This saved model can be reused later for testing, evaluation, or deployment without retraining. That's all for me.
So for the next part is a transfer learning implementation. We leverage a MobileNet V2 for Kuih classification. So why MobileNet V2 is a high performance lightweight model pre-trained on million of image. We utilize it because it efficient and model pre-trained on the image data set. So for the technical implementation, we use weight phrasing. As you can see in the code here, we froze the base layer to keep the pre-trained knowledge. And the next one is the conv 2D bridge. Since MobileNet V2 need a 3-channel, but our data is grayscale, we add a conv 2D layer at the start to convert 1-channel input to a 3-channel. And we also add a custom head here. So this model will also tune with 0.001 learning rate for 10 epochs. Next. So for the result, for the model performance comparisons, CNN versus and MobileNet V2. So for the CNN accuracy, we got about 41.41% current run, but the best run that we do is around 57.81. And for the MobileNet, it's sustained around 57%. So this provide more stable result because it started with pre-learned features, edge and texture. The simple CNN is effective but more sensitive to the starting weight, which is why accuracy varied between runs. Next. So this is a comparison also for the graph. So the MobileNet, the blue line here, start higher at 37.5 and climbs steadily to a final validation accuracy of 57.81. And for the CNN here, it's very shaky and sensitive. The performance start at 30% and reach a final validation accuracy of 41%. That's all from me.
Assalamualaikum. I will be presenting from confusion matrices part up until the end of the slide. Okay, so now let us dive deeper into how each model makes mistake using confusion matrices. So on the left here, we have simple CNN confusion matrix. You can see some scattered errors across classes, especially between onde and serimuka. So on the right, the transfer learning confusion matrix is much cleaner. There are far fewer misclassifications, and most predictions are concentrated on the diagonal where they should be. So this visual already tells us that MobileNet V2 is not only more accurate but also more confident and precise in its predictions. Okay, next, for the model performance summary, let's quantify that our simple CNN achieved 89.38% accuracy. That is for 143 out of 160 test images are correct. While transfer learning with MobileNet V2 achieved 96.88% accuracy, 155 out of 160 that are correct. So that's a 7.5% improvement, which in classification task is quite significant. So clearly, MobileNet V2 is our best model. Okay, for the single image prediction, to see the model in action, here's an example prediction. So we take an image of Onde Hill and then pre-process it by resizing and normalizing and feed it to our best model, MobileNet V2. So it correctly predicts Onde with 91.8% confidence. So this shows the model not only works, it works with high certainty. Alright, so for the detailed error analysis, for the simple CNN, the most confused pair was Seri Muka and Onde, with 4 misclassifications each way. So this makes sense that both are green and use similar ingredients. And for the MobileNet V2, the errors dropped dramatically. Only 2 misclassifications between Onde and Seri Muka remained. And while looking at per class accuracy, every class improved with transfer learning, especially Kuih Lapis and Seri Muka, which gained a full 10% accuracy boost. Okay, now for the Q&A, I would like to walk through some of the key technical decisions we made and the justification behind them. Okay, for the Q1, data engineering justification. First, why did we choose 80-20 train test split? Because this is widely accepted standard that gives us enough data to train the model, which has 640 images while keeping a statistically meaningful test set of 160 images for reliable evaluation. More importantly, we use stratified sampling. This ensured that all 4 Kuih classes were represented proportionally in both the training and test sets. So each class had exactly 160 training and 40 testing images. So this prevent class imbalance from skewing our results and gave us a fair measure of performance for every Kuih type. Okay, next is the model comparison justification. Why did transfer learning with MobileNet V2 outperform our simple CNN by 7.5%? This was expected, and here's why. So there are 3 I would like to point out. The first is knowledge, because MobileNet V2 was already trained on 1.4 million general images from ImageNet, and it already knows how to recognize textures, shapes, and colors, transfer perfectly to food. Okay, for the second point is the architecture. It uses advanced structures like inverted residuals that are efficient at capturing visual hierarchies. And the final is color sensitivity. So our Malay heritage kuih are so colorful, like green onde and layered kuih lapis. Because MobileNet V2 uses RGB input and leverages color as a key feature, while a simpler CNN might not use color as effectively. So in short, MobileNet V2 started with a head start in visual understanding, which our simple CNN had to learn from scratch with only 800 images. Okay, next for the hyperparameter tuning analysis. So for our simple CNN, we use Keras Tuner to systematically find the best settings. So we focus on 3 parameters. Okay, so for the first one is learning rate, on how big the training steps are. Too big and overshoots, too small and it's low. And the second is number of filters, how many features the models looks for. Okay, for the third one is the dense units, which is the capacity of the final decision layers. The best combination was a learning rate of 0.0001, 64 filters, and 256 dense units. This balance allowed stable learning without overfitting our model's dataset. So without this tuning, our CNS performance would have been even lower. Okay, and for the final part is the error analysis. Okay, so looking at the confusion matrices and error patterns, why are Onde and Seri Muka most confused? Because both kuih are green, made from pandan, and both use glutinous rice. For the model, sometimes latches onto color and misses that one is round and the other is rectangular.